Hi there, I'm Shelly Hunt. I work at SAS Institute as a data scientist within the agricultural organization. Today I'm going to show off a kind of prototype decision support tool that we could develop and deploy to put into the hands of ag retailers or growers or researchers at these universities who run OVT trials. So what you're looking at here is essentially the prototype report that we would put into the hands of growers or researchers or the stakeholders of interest, essentially. So we're going to look here. We have a form over here on the left-hand side under Run a New Scenario. The user of this application would be able to select and input different environmental inputs and growing conditions or cultural management practices that they employ to be able to create a brand new prediction. Once they hit submit, in the background, a machine learning model is running on the fly every time that hits submit. This is all being done on the SAS Visual Analytics and on our analytical platform, SASVIA. And so it's a very advanced analytics platform that I love to use and play around with. And so they don't have to worry about using any computational resources locally if they're using the system. It would all be done processed within the cloud. So for example, they would hit submit, they run the scenario, and you can see the results on this page here for this previous scenario I ran. I have kind of unoptimal soil potassium and soil phosphorus levels. I have no irrigation throughout the season. And you might look at this variable and be like, well, what the heck is temp min 5DAP 115? Don't worry, I will get into that at a later point. Ideally in front of a grower, this would say about late season minimum temperature and late season maximum temperature. So in this scenario, compared to what has been observed in the past, I kind of put this higher than average. So it's a bit warmer and we're not irrigating and we have very low soil fertility levels within our soil type, which is sea silk sandy loam in this case. We can see we have a list of predicted yields at the bottom along with the cultivar. So we're testing out every single possible cultivar that has been tested as a part of the official variety trials and the data that we have in our data bank. And we're testing out and trying to make future projections on those cultivars. So given the circumstances in our scenario analysis, what's going to rise to the top in terms of higher predicted yields? So we can see the cultivar names up here, LL6314S, kind of rises to the top. I have this word cloud, which would kind of be the end product, the most easy to digest piece of information for the end user. It is colored in terms of profit. So at the bottom in this table here, you can see I'm taking into account seed cost per acre, farm gate revenue, and of course profit at the end, which accounts for the cost. I have a little slider up at the top as estimating what the soy price is in bushels per acre that they would get on the marketplace. And then, of course, a total amount of acres we are assuming to be planted in soy. And so the size of the best 5 cultivars is in terms of the predicted yield, but that color is going to be the highest profit. So it'll take into account the cost. This is probably the best seed for that grower to plant for the next season, assuming that our projected weather forecast hypothesis ends up being correct. So one of your first questions might be, what data am I looking at? So this data comes from the University of Georgia, their statewide variety testing program. It's 4 years worth of data from 2016 through 2019, provided by Dr. Daniel from the Ag Data Commons. So we have germplasm submitted by commercial entities plus experimental entities at the research stations there in Georgia. It's grown across 7 different research stations farms. So you can see those plotted in this interactive geomap I have here within my report. Next, I kind of want to talk about the current stage of how people use OVT data, official variety testing data. So I've done, like I said, a lot of work with research organizations as well as companies. And there's not a lot of advanced analytics being used out there in this case. If you're really lucky, they might be running a simple ANOVA summary, or we're looking at differences across means. And that's represented here by these box plots. So that's current state. Where I want to help take agriculture and the production as a whole is from simple summary statistics and maybe doing an ANOVA and kind of scooting them along to doing some predictive supervised machine learning. But not right off the bat. we have to do some weather processing first. To beef up my models, instead of just having the inputs we've talked about thus far, the soil type, the location, and the variety type that we're planting, soil information, I want to also beef up the model with some inputs on weather. So I've used the NASA Power API to download weather data, time series weather data for each of my 7 research farms here. So as I'm clicking on each location, you can see how the time series, temperature, and degrees Fahrenheit changes and shifts across the different locations. So if you noticed, I had a lot of time series data in there, and if I want to join it up with my tabular OVT data, official variety trials data, and create a machine learning model, I'm not doing time series forecasting. I need to get it into a tabular shape that will be able to accommodate the type of models I'm going to run. So I'm going to explore different means of aggregating or combining and chopping up and processing my weather data to reduce the dimensionality and include it within my models. So I chose the method of taking 5-day window aggregations across the entire growing period, starting at planting date. And so the naming convention here, 5DAP0, means that I'm doing 5-day windows. DAP is day after planting, and then 0. So this is 5 1-day windows starting at 0. So it'll be 0, 1, 2, 3, 4 day after planting, that average, sum, min, max of whatever temperature or environmental weather variable I'm looking at. So here's a little snippet of the code I wrote just to join up and calculate these kind of rolling windows. And then I have hundreds of input variables, and I have to do some dimensionality reduction. So now we're looking at an automated explanation object within the SAS Visual Analytics. And in the background, it's running a gradient boosting variable selection algorithm. On the left here, we just have a relative importance chart. And for each of the relative importance, we can look at the partial dependency relationship between our response variable, in this case yield, and that relative or that variable from the relative importance chart. But just based off of this really quick analysis to get a prototype up and working, I chose the temp max 5DAP 115 and temp min 5DAP 115, as well as with some other input variables to create my models. Now we're going to move on into the modeling stage of this project. If you recall from the prototyped AI-driven decision support tool, the user never saw anything about a model or an algorithm, but just know that they are supplying inputs to score a new prediction from a model that's running behind the scenes. And so I'm just going to walk through kind of how my thought process went through the initial stage of model building, all the way through choosing a champion model. I don't show this, but after I chose a champion model, I deployed the score code, and it is running automatically every time that form is being submitted. So I started off with a few linear models. We're first looking at the generalized little linear model here. And on the left here, if you can kind of see in this bar chart, we have the list of the names of all the input variables from this model. We have the 2 temperature variables about 115 days after planting. So that's into the 3rd month of the growing season. We have that categorical soil fertility value for phosphorus and potassium, along with the cultivar name and the soil type name. Additionally, we have a cultural management practice in here, the total amount of irrigation in inches, if any. We had a kind of distributed mix of rain-fed trials as well as irrigated trials in this data set. So the linear regression, you can check out the residual plot here. It's looking pretty okay. We'd want it to be nicely balanced, kind of randomized across the 0, not leaning too heavy, no pattern or distinct pattern or shape here. But the validation data split, which we did an 80%, 20% train test or train validation split, it's called here, with an average squared error of 93. And keep in mind that's squared bushels per acre. Moving on to some nonlinear modeling, to really quick neural network. We can see the neural network diagram right here with one hidden layer. We have validation average squared error down to 59.9, so that's closer to 7.6 bushels per acre. But the decision tree gets a little closer at about 7.2 bushels per acre in terms of error. So we've already seen this once, and we're going to take a look at it again. The final tool. And so let's go ahead and run a new scenario in this case. We're going to stick with Cecil sandy loam as our soil type. Let's now give a little better soil fertility values. Higher, we're still going to stick with rain-fed and not as high of temperatures for our minimum and maximum temperatures. So if we looked at the observed values for all of these, this is going to be a bit about average, 60, 95, maybe a little below average. So this is just me as a grower assuming. We know we can't tell the future, but there are some really good long-term forecast models that are out there. So me as the grower saying, I think it's going to be about an average season in terms of temperature. Okay, so our models have run and the tool has updated. We can see here in this highlighted column, predicted yield, we were seeing values in the 50s as maximum, and now we are seeing a high of 85 bushels per acre. Then I'm going to go over and look at sorting it in terms of profit from highest to lowest. And notice it's this really big green-blue cultivar here, P55A49X. It is providing both the highest profit and the highest predicted yield in bushels per acre. Let's say, for example, we can adjust the soy price. I just know off the top of my head, the soy price is closer to $14 a bushel. And so now this is probably a more realistic update for this current markets. And if you are perhaps have different values of acres, you can tailor that to adjust it to be closer to what you as a grower, you as a user would actually see. So now we have still our best cultivar here with this nice hefty profit in this scenario case.